Hello everyone and welcome to this lecture. Today we are going to talk about how we can diagonalize a matrix, and this will be fruitful in many of our calculations. And recall that in our past lecture, that is the previous lecture, we talked about similarity transformation, and using that similarity transformation we are going to diagonalize a matrix. So how can we do that? In fact, this diagonalization is not only valid for finite dimensional operator. You can define a similar situation for infinite dimensional operators as well, something called a spectral decomposition and that. But let's focus on matrices, that is linear operators with finite dimensions, a finite dimensional vector space. So what we're going to do now is that we're going to consider a linear operator. So let's write the linear operator A on that is represented in some basis, that is represented in some basis EI, where I equals to 1, 2 and n. Note that we are not using the Dirac notation today, but equivalently you can write them in Dirac notation. So to keep life simple and to make use of the index notation, we are going to not use the Dirac notation today. So the reason why I'm calling this linear operator is represented in this basis, because recall that our matrix elements are basis dependent. So that's why I'm first considering a basis with EI, and what I'm going to do now is that I'm going to use a similarity transformation to define a new basis. Let's call them with J, and this is given by sum over I Sij EI. Notice that this upstairs downstairs it doesn't matter as long as we have a Euclidean matrix, and that is something we are not going to discuss today. So just you can always, instead of writing it upstairs, you can write it downstairs. So let's do that. So this is our initial basis. Then we do this similarity transformation, and this is our new basis. And this new basis will be something that we want our matrix to be diagonal. That is, when you use the new basis, our matrix elements will be diagonal. That's something we want. So let's do that. We demand that the elements of A will be, okay, let's not write elements of A, it doesn't sound right. We demand that the operator A will be diagonal in these spaces. So this is our demand. And recall that our eigenvalue equation, that is, if this operator is represented with some matrix, then we can write the eigenvalue equation for this as, let's see in the component notation, something like this. Here lambda j is the eigenvalue, the jth eigenvalue, and this xj is the corresponding eigenvector. And we really want to see whether taking xj, that is the new basis over here, which is the eigenbasis, whether it will transform A into a diagonal form. That is, first we have to construct A in some manner, that we'll see in a few seconds, and then we want to transform from the initial basis to the eigenbasis, and we want to see whether our matrix actually becomes diagonal or not. We expect that to be true because the eigenvalue matrix itself is diagonal, and we want to see that whether some similarity transformation will allow us to do that. So recall that from previous lecture that A prime will be S inverse 1. This was our similarity transformation. And we propose that S will be built out of, okay, let me just write it first. S will be built out of the eigenvectors of A. This is something we propose. So accepting this proposal will give us the following matrix. Let's say the first column will be the eigenvector x1 that will correspond to the eigenvalue lambda 1. The second column will be the eigenvector that will correspond to lambda 2, and so on and so forth. Also notice that we are assuming it's a non-degenerate case. We will talk about what happens in the degenerate case later. So for now, this will be the structure of this S, and we want to see that whether this A prime is diagonal. So let me just write that down. We want to see if A prime is diagonal. So let's try to see it. And first, what we're going to do is that we're going to introduce something, that is, notice that S is built out of the normalized eigenvectors. You can always take the normalized eigenvectors, and these normalized eigenvectors are x1, x2, and so on. So any element of S that will be denoted by Sij can be written as the column vector. So remember that, or recall that this I was corresponding to the row and this J was corresponding to the column, right? So any element can be written of any element of Sij can be written as S of J, that is the column vector, and take the ith component of the column vector. So let's say you have S as 1 0 0, 1 0 1, 2 3 5. So you write Sij and assume that these are some eigenvectors of some operator, something. So you want to have, let's say, instead of Sij you write, let's say, S13. So by this notation over here, that is on this side, on the left hand side, we need to take the third column first, that is this column over here, and we want to take the first element, right? And this is our first element 2. So the third column and taking the first element. So if you write it like this over here, this will be just this whole thing, the third column. Write the third column, and then we select the first element. The first element is 2, so this is 2. Also this agrees with this. So this is the notation that we are using over here. Now let's try to see what happens when you use this similarity transformation using these notations. That is, first we want to see any element of S inverse, or let's say SAS inverse. This can equivalently, I should have written it like this from our past lectures, that A prime will be S inverse 1 AS, not SAS inverse 1, or vice versa. So this should be rather S inverse 1 A S, and we want to see any element, that is the ijth element. And if you recall how we use the index notation when it comes to standard matrix multiplication, you can see that there will be, let's say, two dummy variables over here which will get summed over. So you have S inverse 1 ik A of kl and S of lj. But now use this notation over here. Let's call this equation 1 so that you can understand what I'm saying. So now we are going to use equation 1. So if you do that, you will have S inverse 1 as ik A of kl, and S of lj will be represented with x of j and taking the lth element, right? Yeah. And now comes the tricky part. The tricky part will be to use the eigenvalue equation itself. So how can we do that? Recall, this is our eigenvalue equation, right? That is for x of j corresponded to the eigenvalue lambda of j, and now we are going to use that. So here you have this operator that is in the component notation, and if you use the eigenvalue equation, then this will be lambda of j and x of j l. I mean, let's write it down first so that we don't get confused. So this is kl. Okay, put a comma over here. S inverse 1 ik, right? And first we write the, because if you just get rid of this index notation, this is just matrix multiplication like this, S inverse A of x, right? That's how it would seem schematically. So we have our indexes ik, kl and jl, and this will give you just lambda x itself, right? And again you can write this x in terms of S inverse S, and then this S and S inverse would cancel out. So this is what we're going to see in the index notation. So let's try to do it. Or instead of just writing in the index notation, you can also switch to matrix notation right now, and that would be even more convenient. But let's stick with the index notation for this bit. And if you write it, this will be lambda of j. Why? Because you see that all these dummy indices are getting cancelled out and this j index is surviving. So if you can write it in a matrix notation, this will be just S inverse A x of j, right? And from here you will have a lambda of j x of j. That's the thing we did here. That's why we wrote lambda of j. And after writing lambda of j, what we have x of j l. And now we are going to use equation 1 again, but now we are, instead of keeping this x of j, we are going to put back this s. So how do we do it? Write k of l, S inverse 1 ik. This lambda is just a number, remember that. It's the eigenvalue, right? It's just a number. And there is obviously an identity matrix over here, but it doesn't do anything. It's just there. It doesn't do anything, and you will see soon that you don't even need to introduce the identity matrix explicitly. So okay, oh sorry, the index should not be L, it should be K. Because you can see that, oh no, not this one, sorry. So this is a tricky part of this whole index notation thing. You have to keep track of your indexes, and the reason is coming from the matrix multiplication, because if you just use this whole thing and when you matrix multiply it, this L, that is the columns, will get cancelled out and this k index will survive, and after that you will have this x of j with k. And if you now use equation 1 and notice how these indexes were arranged, then you can keep track of your indices easily, and this will be just s of kj. So this will be just s of kj, because just notice over here that whatever index went on the inside of x, that is the column index, and the row index was outside, right? So that's what is happening over here as well. So this is our column index, this is our row index, and we have this. Since lambda is just a number, you can, and there is no summation over j, you can pull it out. Lambda j over here, you have kl, and this is just s inverse 1 of ik, s of kj, and this is what? This is just sum over, let's say I'm getting rid of this k thing, and obviously I should get rid of the l as well, because this l got summed over before. I should have gotten over this thing, because see here, let me just highlight it down again. Here l is getting summed over, and that's why in the next line we don't write l, and after this l is getting summed over, the only index left is k. So this is another way you can keep track of your indices, but as long as you know what you're doing, you're just fine. You can also just do it in this matrix notation. That's far easier than this index notation. So finally you have this thing over here. There is lambda j, there is k, and finally you have, this is just a delta function, that is one matrix is multiplied with this inverse. So this should be an identity matrix, and in the index notation this is just the delta function, right? So this is just lambda j and delta I j. So S inverse A S of ij is just this. Whenever I and j are equal, there is some lambda, and if I and j are not equal, it's just 0. So this S inverse AS will look something like lambda 1, lambda 2, lambda 3, dot dot dot, dot lambda n. Also notice and recall that we are not considering the degenerate case. So our proposal was correct, that if you define a similar matrix or some S matrix with the columns as the eigenvector, that is, you take the eigenvectors and you stack them up in the columns when there is no degeneracy, and if you find its S inverse, then you can easily diagonalize a operator or a matrix, and the diagonal matrix will be nothing but the matrix with the eigenvalues. So this guy over here, it's called the eigenvalue matrix. And there is a nice geometrical picture of it. The geometrical picture will look like the following. Let's say this is our initial basis. So red means initial basis, and let me choose the green color. So I'm just trying to draw a three-dimensional space. So now let's say you have three cross 3 system. So there should be 3 eigenvectors, and these are our 3 eigenvectors. So what happens is that, let's say this is 1, this is 1 prime, this is 2, this is 2 prime, this is 3, this is 3 prime. So this 2 gets rotated to 2 prime. This 1 over here, it gets rotated to 1 prime, and this 3 gets rotated to 3 prime. So this green will be our eigenbasis. We call them eigenbasis. And in this eigenbasis, this initial basis vector, they just rotate and overlap. That means they coincide with the eigenbasis themselves. So that's why we get a diagonal matrix. before I finish off this similarity transformation, again I want to emphasize that the physical information is invariant under this kind of transformations, and in case you have a Hermitian matrix, this similarity transformation will correspond to a unitary transformation like we saw in our earlier lectures. So this will be it for today, and thank you.